Good afternoon. Welcome to the medley session. So we have 4 very diversified and exciting talks. We just don't have a common title to summarize all of them. Let's start from the first one, guided equality saturation. Our speaker is Thomas Kœhler. Go ahead.
Thank you. So this is joint work with my colleagues Andrés, Siddharth, Tobias, Phil, and Michel. And Michel and Andrés are here with us, so don't hesitate talking with them later. I will start with an example, which is about reducing memory usage in a functional program. So let's say that you want to do this by introducing the rewrite rule on the left, also known as map fusion. And you want to apply this rule on the program that is shown on the right. The problem is that you can't directly apply this rewrite rule because the left-hand side of the rewrite rule is not in this program. But we can do something about it. We can add 2 more rewrite rules. So rewrite rules 2 and 3. And even though they have no effect on memory, they still allow us to reduce memory usage because they enable applying the first rule after applying them. So on the right, you can see that rule 2 and 3 are applied, and then that allows us to apply the first rule twice. The problem is that this rewrite path, it will not be explored by a technique like greedy rewriting because the memory is not reduced by these rewrite rules. So there is no local progress. So what we can do is using equality saturation instead of greedy rewriting. The idea of equality saturation is to perform the rewriting on an equivalence graph instead of an E-graph, or E-graph, sorry. When we initialize it from the input term, it looks a lot like a standard abstract syntax tree. But it becomes interesting when we apply a rewrite rule for the first time. So here we apply the second rewrite rule, and instead of replacing the left-hand side of the rewrite rule with its right-hand side, we simply record the equivalence between the 2 sides. So as is written on the slide, transpose map map G is equal to map map G transpose. And that's why now in the graph, we have an additional node which is in the same equivalence class as another node. So here the equivalence classes are represented by these dashed boxes, and the solid boxes are almost regular nodes. We can keep applying more rewrite rules in this way, and at this point the E-graph efficiently represents many equivalent terms because it is doing a lot of sharing. So we have a lot of nodes that are referring to the same equivalence class, and each equivalence class encodes many equalities. So if we want to finish optimizing our program with equality saturation, we need to extract a term from this E-graph. Here we are going to extract a term that minimizes memory usage. And it turns out that it's the term that we had on the slide earlier, the global optimum map map FG transpose. So equality saturation has a lot of benefits because it allows us to explore past the local optimum compared to greedy rewriting, but it also has its own limits. And we can see them by complicating the example a little bit more. So now, instead of simply reducing memory, we're interested in applying an additional optimization, which is known as tiling. And that, to be brief, is used to improve memory accesses. So we add rule 4 and 5. And now we can perform things like one-dimensional tiling. So one-dimensional tiling is very easy to apply using equality saturation. If you look at the graph on the right, which shows the memory footprint, you can see that we're not using even a megabyte of memory. and a single iteration of equality saturation is sufficient. So what is an iteration here? An iteration is when you apply all the possible rewrite rules to the E-graph once. So typically, equality saturation works by growing the E-graph iteration after iteration. So one iteration is very simple, but we can make it more challenging by increasing the dimension of the tiling. So if we want to perform two-dimensional tiling now, this becomes more challenging. So before, only applying the fifth rule was sufficient to achieve the tiling, but now we have to combine the fourth and fifth rule with the first ones to achieve our goal. As you can see with the colors, the transpose functions are coming from the fourth rewrite rule, and the split and join functions are coming from the fifth rewrite rule. Now we can, if we look at the memory footprint of using equality saturation to achieve this goal, it takes 6 iterations, and we are using a couple of megabytes of memory. And when we go to the third dimension of tiling, that's when things blow up. So now, after 8 iterations of equality saturation, we observe that the E-graph grows extremely rapidly. And in fact, we exceed our 8 gigabytes of memory without finding the goal that we're looking for. So this shows that while equality saturation is very powerful, it can also be very expensive when you try to scale it out. So to summarize the problem, we are trying to achieve a final goal using equality saturation, but we are running out of resources before achieving our goal. So what can we do about it? And that's where our technique-guided equality saturation comes in. So the idea is that if you are not able to achieve your goal with the fully automatic equality saturation, you can ask an expert to provide guides or intermediate goals, and in this way break down a complex equality saturation search into a sequence of easier equality saturation searches. So now, instead of failing to find the final goal, we can find it thanks to the intermediate goals. What does this look like on the 3D tiling example? So at the top of this slide, we still have the same program that we started from in the 3D tiling case earlier. But now, instead of trying to directly find the tile program at the bottom of the slides, we are introducing this intermediate step. So the guide here provides the insight that to apply tiling, it's actually easier to first split the maps before reordering them. So we are decomposing this optimization in 2 stages. And actually, a guide does not have to be a complete term. So we allow guides to be more or less precise sketches. And you can think of sketches as incomplete programs. We still guarantee preservation of semantics because we are still applying semantics preserving rewrite rules. So we don't need to worry about allowing invalid programs using this guide. So with these single guides, we actually make 3D tiling reachable. On the left, we have the unguided search, which was using more than 8 gigabytes of memory and failing. And on the right, we have the guided search. So now we actually have 2 equality saturations that are running. The first one takes 6 iterations to find the intermediate goal. And the second one takes 7 iterations to find the final goal. So we can scale this our approach even further by looking at matrix multiplication optimizations from a compiler which is called TVM. So TVM is a specialized compiler for machine learning, and it has a tutorial in which they explain how to optimize matrix multiplication in their framework. So with TVM, the optimizations are also not fully automatic. There is also some form of semi-automation. And the optimizations that are applied include tiling, which is about transforming loops, but also other optimizations that change data layout and add parallelism. There is prior work that already showed that it's possible to express these optimizations by manually composing rewrite rules. And now what we're interested in is automating this process using guided equality saturation. So these are the benchmarks for unguided equality saturation. Here we have 7 optimization goals of increasing difficulty. So the baseline is very easy to find. The blocking goal is similar in difficulty to the tiling goal that I showed you, but this time on the bigger program because it's matrix multiplication. And then we have more and more complex optimizations that are layered on top. And we can see that the 5 most complex optimizations for matrix multiplication are too hard to find without guidance. You can also see on the right how the size of the E-graph grows extremely rapidly, as we've seen before. Now, if we use our guided equality saturation technique, we can find all of these optimizations with at most 3 guides. And each guide is eliding about 90% of the complete program, so it's 10 times smaller. We can also compare the runtime and memory consumption for the second goal because it was the most complex one that was found without guidance. And with a single guide, we are actually able to find this optimization 582 times faster using 116 times less memory. We have a second case study, which is about showing that we can go beyond program optimization with our technique and actually implemented a tactic for the lean theorem prover. And what is nice about this tactic is that it allows you to write your theorems by focusing on key reasoning steps. So here the blue box is guides for our technique. And compared to the proof that you would have to do if you were applying every rewrite rule by hand, this allows you to omit a lot of steps and details. So you don't need to mention which rewrite rules you're using, and everything that is in green here is inferred for you or discovered for you. We pushed this to slightly more complicated theorems. So we prove theorems on rings of characteristic 2. For the theorem on the left, you can see that we have a comparison of guided and manual techniques. And we can see that the guided technique is much faster than the unguided technique, but at the same time has a negligible overhead compared to manually providing all of the rewrite steps. For the theorem on the right, we compared what happens when we change the amount of guides. So we had, initially, we came up with 5 guides, and we decided to see what happens if we don't use some of these guides. So we tried all the combinations, and it turns out that actually one good guide is enough. So it's very important to choose your guides wisely. To conclude, guided equality saturation offers an effective trade-off between manual and automated rewriting. For program optimization, it enables expressing optimizations with guides that resemble explanatory code snippets. So something you might do when you're writing a paper and you're trying to explain your optimization to other people. And for theorem proving, the guides resemble the key reasoning steps that you might find in some textbooks. If you're interested, we have more details in our paper. We also have supplementary material with all the programs and the guides that we used for these experiments. And our code is open source. Thank you.
Hi. One of your examples is the Frobenius morphism in a field of characteristic, or in a ring of characteristic 2.
Yes.
Of course, it generalizes to rings of any characteristic, but would this have an impact on the complexity of is there something in the characteristic of the ring that would impact the performance and the speed of the approach?
So are you talking about proving it for different instantiations of the characteristic, or
yes,
for a generic characteristic?
For different instantiation of the characteristic, would it change execution time? Would it increase execution time? Does it depend on it?
Maybe Andrés can answer this question. So Andrés worked on the theorem proving case study.
Yeah, thanks. As a disclaimer, that was just to find an example where you needed a bunch of rewrite rules. I presume it would not change that significantly because you just have a different. So you can encode that as one rewrite rule where you say basically 1 + 1 is 0, and if you have a different characteristic, you might get a few more. But yeah, I don't think that would. It's obviously, yeah. There's obviously much easier ways to do this. This was just to have a large set of rewrites to test it.
So, question here. So I was wondering whether these intermediate human-provided guide sketches that you have, do you know if they have any particular property that distinguishes them, which one could search for automatically? Do they have any, even though they may not immediately be clear how to find them, are there characteristics that you know about what they should satisfy?
I think that's a good question. And so the first answer I would give is that the entire point of allowing the user to provide these guides is that in the general case, we don't know how to find them. And to find them, you need domain-specific insight. But I think that there is definitely interest in automatically finding these guides for specific domains. So for example, if you think about tiling, you could easily automatically infer the tiling guide if you know that in the specific rewriting problem that you're looking into is about tiling.
Hi, right here. Thank you for the talk. I'm really excited by this work. I was wondering whether you could comment on how much your method relies on the particular framework that you use for quality saturation. And in particular, I know recently there has been some work in implementing equality saturation in data log, and wondering whether your technique could be ported to that.
Yes, that's a good question. I think there is no fundamental reason that prevents you from applying this technique in another equality saturation implementation. And actually, I think there are even many more opportunities if you think about the data log implementation, because there is an implementation of equality saturation called egglog, which is about implementing equality saturation using database theory. And I think that it would be very interesting to think about expressing guides as database queries. So I would say it's possible, and maybe even allows even more a richer language of guides.
So one of the advantages of sketches, in addition to just, you don't have to think as hard because you don't have to think through all the details, is reusability, right? The fact that if you have lots of problems that kind of share similar structure, they can all share the same sketch. But sometimes you have to engineer these sketches a little bit if your goal is reusability. I wonder if you can comment a little bit on this.
Yes, that's a good question. So actually, I can quickly show that we have some sketch abstractions that we use in our experiments. So here, for example, without going into the details, we have this def contains add mo, which defines sketch by composition. And we have also defined other sketch abstractions in this way. So although the for different performance optimizations, you will write different sketches. You can still define abstractions by compositions and reuse them in your different optimizations. And I guess the second, beyond these abstractions, we also noticed that for the different optimizations that we are looking at, we have a lot of intermediate goals that we can reuse. So we don't have as many sketches as the sum of the sketch guides in this table.
We have last question there.
How do you see apply this work in a rewriting system with backtracking?
Can you elaborate on?
Well, you talk about greedy rewriting.
Yes.
And when if you I don't know, use some sort of backtracking, you can certainly say that I solve part of the phase scheduling problem.
So I guess there are. Yeah, maybe we can. I can answer this question after.
Sorry.
All right, so let's thank the speaker again.